Good morning, Science 20s. Our lesson today is going to be an application of the concept of impulse, or as you would also know it, a change in momentum. We are going to apply this idea of impulse to safety devices, and the ones we've chosen are going to be those safety devices in vehicles. So we're going to talk about airbags and collapsible frames and bumpers and seat belts. Well, what I want us to think about first is why is it less painful for us to catch a baseball when with your bare hands when you give catching the ball compared to just sticking your hands out and catching it with firm rigid hands? What is it in this give that allows it to be less painful catching the ball? And what I want us to realize is that, and I'm just going to trick my device into working here. What I want us to realize is I want us to remember that the formula for impulse is change in momentum equals force times change in time. Well, if we're trying to figure out why the force is less, then let's move the formula around. So we're solving for force. So we're going to have momentum or impulse divided by time. And this is an important concept to think about. When the baseball is coming towards you, it has a certain amount of momentum. That momentum isn't going to change. It's coming in at with the same momentum into your hands. Therefore, the only factor you can change is the amount of time it takes to catch the ball. So, when I come in with these soft hands and I give, my time is going to increase. And when I increase this time, when I divide my momentum or my impulse by a bigger number, I'm going to get a smaller amount of force, which means that ball's going to hurt less because it's applying less force into my fingertips. So, how can I safely change momentum or impulse? Well, in some instances, the change in momentum is provided by a very large force over a very short period of time. For instance, in a car crash, if we were to go back and we have no airbags and we have no safety devices at all, and we were to, let's say, run into a tree, that would be a very strong force and it would hit our bodies in a very short amount of time. That's going to be a big momentum. Well, there's the opposite of this as well. In order to also have a large momentum, we could also have a very small force over a large amount of time. Because remember, multiplying these two numbers together, big number, or small number, big number, we're still going to get the same amount of momentum. So one of these would have to change. Well, the force experienced will decrease if we change the amount of time to something longer. So I have car A and car B. In this scenario of car A is traveling at 100 kilometers per hour. Well, if it has more time to slow down, so if it increases the amount of time to slow down, it's going to have a much smaller momentum here than in B, where B is traveling also at 100 kilometers per hour, but all of a sudden it hits a brick wall. So it has very little time in order to slow down. Therefore, it's going to carry through with more momentum. What I would like us to do is let's watch a safety video about this smart car and the changes they've made. Pay close attention to all the little safety features because we will need this on the worksheet later.
The key to its defences is its so-called tritium safety cell, a rigid steel cage reinforced at key points. Smart describe it as the hard shell of a nut, with small but efficient crumple zones both at the front and at the rear. In theory, getting inside is like putting on a suit of armour. Even when it hits something more than twice as heavy, the bit where you sit is remarkably unaffected. There may not be a long crumple zone, but look how the Smart's windscreen remains intact. This is testimony to the rigidity of the passenger cell.
The downside of the shell's rigidity is that there's a greater potential for the crash forces to be transmitted through to the passengers. Ideally, you want to slow them down as gently as possible. So you get seatbelt tensioners that stop you lurching forward violently, and they're fitted with force limiters that give you a bit of slack before they dig into your chest. The car's also fitted with a driver airbag, a passenger airbag, and a steering column that will retract out of the way in a crash to give you more room to slow down.
That's the theory, but no one knows how the car will behave when it's crashed at 70 miles an hour, which is where we come in.
We've enlisted the help of engineering guru Dr. James Bryson. His team have converted a Smart so that the brakes, steering and throttle can be operated via remote control. Dr. Kim Blackman will guide the Smart from a chase car straight into 20 tonnes of concrete block. It'll be similar to losing control at 70 miles an hour and spilling off into the temporary barriers on a motorway. Surely now the Smart has met its match.
Kim to James, 10 seconds. 10, 20, 30, 5. Give me straight, Make it. 40. 5.
From 70 miles an hour to naught in 1 second. Energy that it moved 20 tons of concrete, leapt into the air and rebounded to the side of the road. We didn't know what we'd find when we reached the wreckage. The steel cage has certainly done its job really well. You can still see the original shape, just that one nasty kink there. Don't forget, this is a car without a roof. The plastic was just shattered. So without even the strength of the roof, there hasn't been that much effect. You can in fact open the door. Bits fly out. And it's only really when you come around the front, you do see that massive impact. Around the other side, though, it still looks remarkably like a Smart car. You can see the full shape of the door. Indeed, the door not only opens normally, it closes again. So that does show how well that cage has worked on this impact.
We were staggered at how well the Smart seemed to have stood up to our high-speed collision, but couldn't help wondering how a conventional small car would have performed in a similar test. So we found out. Another remote-controlled 3-star NCAP car, 70 miles an hour, into concrete blocks. Without a super stiff structure like the Smart, you can see how this car's bodywork ripples as the shockwave dissipates. But again, the body looks remarkably intact, given the huge energy involved. Closer inspection revealed that there had been some intrusion into the footwell, but in comparison, the Smart looked to have suffered even more.
Perhaps most surprising was the obvious energy-absorbing qualities of the concrete. The Corsa's greater mass moved the blocks more than the Smart, but in both cases, the concrete didn't necessarily deliver the killer blow you might have thought.
But here's the rub. The cars may have stood up to the severity of the crash surprisingly well, but the humans inside wouldn't. No matter what you drive, rapidly decelerating from higher speeds is something your internal organs simply cannot cope with. The chilling truth is, the people inside both cars would have been very unlikely to have survived.
So, how much stick can a Smart take? A lot. But that can't be said for its passengers.
So that video was rather shocking. They did a comparison between the smart car with the steel cage inside compared to a standard car with less of that cage. So our question is, how do we incorporate this idea of change in momentum or impulse into a vehicle? Well, they mentioned a number of things on the video. They mentioned the crumple zone of the car with the steel cage, where this is the spot on the car where they're trying to protect you, because this is the spot where the passengers are. Um, Again, the back of your car crumples, the front of your car crumples, and really that crumpling is set up to slow down your vehicle in order to increase the amount of time so that momentum will decrease. Same concept with guardrails, right? If you get over on the guardrail and you're making that much friction along the side, it's to slow you down. It's to actually make your vehicle increase the time interval in order to decrease the momentum or the impulse of your vehicle. Same with airbags, whether they be off the steering wheel or passenger or even side airbags in a vehicle. All these things, your bumper, it's got that little air gap there, give. So it's going to give a little bit, and we're going to lose some energy there first, which is going to slow us down. This video is a comparison between an airbag versus a non-airbag. I want you to concentrate on this one, not about the car. The car is going to be wrecked in both scenarios, but I want you to concentrate on the person driving the car, the dummy in this case, and take a look at how much time is added when you added an airbag. There's no volume on this video, so I can talk through it. So non-airbag, body goes straight into the vehicle. All that force goes into the steering wheel. In this one, now we have an airbag that's deployed, and you can see a much more or less, if you want to use the word softer landing, as it slows down. It's almost like a cushion, and it gives a little bit and slows down the direct impact on the body as we go through. It's just shocking. You kind of get caught off guard and have to watch it for a second. So, because most people come in and they don't know a lot about airbags, and you're at the age where driving is important to you, I just wanted to give you some information. Airbags are rolled up inside the steering wheel, dashboard, or sidewalls of a vehicle. There's a sensor in the car that sends an electric signal to ignite a chemical, sodium azide. This sodium azide decomposes really quickly, and it releases nitrogen gas that fills up that airbag to reduce your passenger speed and your momentum safely. So again, very quickly, there's a decomposition reaction, and all of a sudden we're collecting a pile of nitrogen gas, and that inflates that airbag. Reminder, think about what momentum is, and you've seen me move the formula around move it around to solve for other variables in momentum. In order for us to decrease the force, since I can't change the momentum of the vehicle, what we do is we put in these safety devices that will increase the amount of time. By increasing the amount of time, we're going to decrease that force. And so this airbag is a perfect example of that. Now, the problem with an airbag, though, is that it's gone through some generations, right? Airbags, when they first came out, are not as good as they are now. The first generation of airbag was designed with the idea of an adult male in mind, which meant it inflated too big, too quickly, and therefore it caused injuries to smaller people like women or children in the car. And so the airbag, a lot of people were like, oh my goodness, airbags are very, very dangerous. But then came along the second generation of airbags. And these guys have been designed to inflate less so that they're a little smaller, and to inflate a little bit slower so that it takes into account a smaller body shape than a male. And then now we have a third generation of airbags that have seat sensors that actually will detect the mass of your occupant. So the size of the occupant sitting in the seat, and it will adjust that airbag accordingly so that bigger human, bigger airbag, smaller human, smaller airbag. Now, the one thing I want us to realize is no matter what type of airbag we have, even this tertiary or third level airbag, you never place a small child or car seat in the front seat of your vehicle because the force from that airbag can still kill that small child. This video will have poor volume, but I think you will see the impact. This is a child sitting in a car seat in the front passenger seat of a vehicle while an airbag goes off. The vehicle's not moving. What the fire department is doing is they are remotely setting off the airbag so you can see the effect.
Ready? 3, 2, 1. I think
That's pretty convincing.
Yeah.
I agree with that guy's last statement. If there's anything that convinces you to never put a car seat for a child in the front seat, that's got to be it. The amount of force that hits that child is unbelievable for the size of that child. Now, the other thing I want to point out is this video does a comparison of, okay, you've now got the car seat in the back seat. Why it is so important to put that car seat backwards so that you are not looking directly at your child. Your child is facing the rear of the vehicle. They're going to do a double comparison, show you what happens in the car seat when your child is faced forward compared to the proper way to install a car seat when your child is facing backwards.
Every year, many car accidents take place at speeds of 50 kilometers an hour. Children are especially at risk, and correct positioning of the child's safety seats is therefore very important. We will now take a look at what happens if your child is sitting forward-facing in a frontal collision. If the child is sitting forward-facing in a frontal collision, this exerts huge forces on the shoulder and neck regions, as well as on the child's head. This can lead to death or permanent injuries as paralysis. If your child is sitting rear-facing during a collision, the force will be spread over a greater area of the body, and there'll be less pressure on the neck, head, and inner organs. If your child sits rear-facing instead of forward-facing, this reduces the risk of serious injuries and death by more than 90%. Children should therefore be seated rear-facing as long as possible, or until they are 4 years old.
By putting your child correctly into the car seat, in the back seat, facing backwards, you are increasing, in case of an accident, your child's survival rate by 90%. That is huge. Now, there are 3 types of collisions. When a vehicle collides with another object outside the vehicle, like a tree or another car, we call that a primary collision. In a collision, when your body, the person driving or the passenger, hits interior parts of the vehicle, that is called a secondary collision. And then when your internal organs of a person in the vehicle make contact with the outer shell of your body, like your ribs, that would be called a tertiary collision. In a collision, all 3 of these are going to take place. Vehicle will hit an object, your body will hit parts inside your vehicle, and then your internal organs will hit parts of your actual body. All 3 of these collisions will take place in a natural, everyday, let's say, car accident. So, looking at these safety technologies, let's see if we can figure out what class of collision they are trying to prevent. So we are thinking about primary, secondary, and tertiary collisions. So shock absorbing bumpers. Well, that's outside the vehicle, so that would be for primary. Oh, forgot to turn my pen on. So this would be for primary collisions. The crumple zone of the frame. Again, vehicle's going to hit something. It's going to crumple on the outside. I would say that is primary as well. The padded dashboard or the padded steering wheel inside, well, that would be to help protect you as you hit a piece of the car. So that would be secondary. Seat belts would again be secondary, but I think they also play a role to protect your internal organs from hitting the ribs of your body. They're going to help slow you down. So I would say this is both secondary and tertiary. And I would say that these two relate the same, where an airbag is also secondary, but it's also tertiary. Hope you found this video informative.